Yeah, so thank you so much for this opportunity for the committee and then this organization. So I'm very happy to be here and to share our research outcome to these experts in the computer science and information technology. So I'm from Iowa State University, USA, and I'm an associate professor in civil and construction and environmental engineering. And then my collaborator, Dr. Jae-Kwang, is professor of statistics. So our team is about developing the data curing tool for general purpose data curing tool supported by National Science Foundation. So I'm here to advertise and introduce our tool for global researchers and experts like you. I'm very happy to have this chance. Right. So our typical problem is incomplete data. So it's everywhere, basically in survey. You may know the last US pre-election, actually presidential election was very, very narrow gap. But we failed to check that through the survey. So we failed to check that the result because there was a misinformation or incomplete data problem. And also if we are entering the climate change era, but the data usage survey sometimes fail to catch the incomplete data issue, they may mislead the government to make a wrong decision, so on and so forth. Not to mention the medical information survey, we have a lot of incomplete data problem. And also in the general engineering and science, we have genome or phenotype data in biology, and then various sensor. We have been expert in IoT, expert here. I believe you have many incomplete data problems. So it's everywhere. Then question is, how can we conduct reliable data-driven research with incomplete data set in such a way to improve the subsequent statistical and machine learning predictions? So we want to help the accuracy. So as a head up, I want to share this result. So from previous research, if we cure the incompleteness with a naive method, I will talk about what is naive method, then the subsequent machine learning or statistical method, such as the generalized additive model, the GAM, or extreme random tree, ERT, artificial neural network, just like deep learning family. If we cure missingness naively, then the root mean square error may be very large. But if we cure nicely or properly, we can substantially reduce that, depending on the data type. Then what is the right naive method to cure data in the typical computer science community? As far as I know, they use a mean value, or they simply delete when the one data instance is not complete. So we call that as a whole a naive method, but it leads to loss of substantial information because you delete that, or it may introduce unexpected bias because you use simply mean value of the observed value. So it may lead to low accuracy in machine learning and statistical prediction and other statistical inference. So actually in statistics field, there are theories already. So they call imputation theory. So one of the most popular imputation theory is so-called multiple imputation. So originally developed and propagated by Dr. Rubin in Harvard. So in sum, they produce from this data, they produce multiple copy of the data set, and they cure the multiple copy. That's why they call it multiple imputation. And they have their own formula to combine them to get the final result. It's very robust and a statistically strong method. But problem is that for general users in engineering and science, it's very hard to meet the assumption of this method. So there are some the statistical and theoretical study about that. The multiple imputation requires so-called congeniality and then self-efficient estimation. It's very hard to satisfy this one as an engineer and scientist. So, and also it's very difficult to use this one multiple imputation for large data set. It's very available in data engineering or science domain. So our group finds solution from hot deck imputation method. Hot deck means we use only the observed data. We don't use any other artificial data. We have, although it's incomplete, we want to use this. So that's why we call it hot deck. And we don't require any difficult statistical assumption, as we have seen. So it's very easy to cure the data. So there are the history of theory about this one. And another good source of solution is the fractional imputation. Fractional imputation means that suppose we have 100 instances, data instances, then each data set have different importance to cure the data. We call that fractional weight of that data. So how can we find that weight or importance of that data? So there is some theory about that. That's why we call that fractional imputation. So in some, we call that fractional hot deck imputation. That's why we call that FHDI, FHDI. There are some theory, so I'm just wanna briefly skip the theory, but the heart of the theory is that when we have continuous data, for example, one variable has this continuous data, then we discretize this as several category. We call that discrete category. We call this discrete G. And then we tackle this categorized or discrete categorized data set instead of this continuous data set, because it's very difficult to deal with existing the continuous data set. And then each box is called imputation cell, imputation cell. So suppose one variable, variable 1 is categorized to G categories, and variable 2 is categorized into H category. Then think about this will make G times H plus 1 category or imputation cell. So we assume that each imputation cell has the mean and its standard deviation. So I want to show you, to understand this better, I want to show you a very simple toy example. So suppose we have 4 variables that we generate randomly with introducing some missingness on that data set. And using, by the way, we already shared this library, FHDI library in the R package, so it's open source. It's already available for the global users, so you can download it. So initially, Y1 has missingness. So out of 100, we have 42, and Y2 has 33, Y3 has 18, so on and so forth, missingness. Then this is the existing data set. So first instance has missingness in variable 3. Second instance has missingness in variable 1, so on and so forth. But importantly, it can have multiple missingness. So instance 4 has missingness in variable 1, variable 3. So we change these to very simple indexes like this. 3, the imputation cells 3, category 2. 0 means the missing. It's missing. So as you see here, 0, 0 means is 2 variables are missing, so on and so forth. And then we have very long list. After sorting, then we have a very diverse missing pattern. For example, it's very serious in this case. We don't have any information about 3 variables. Only we know variable 4 for this case, so on and so forth. Then using, there are two types of approaches. One is called fully efficient fractional imputation. That means we search all the similar category or cell, and then we use all possible donor to cure that missing cell. So suppose we have 6 possible donors, similar cell, then we use all of them by giving them some weight to cure this one. But fractional hot deck imputation, rather than using all of them, why don't we just randomly choose or some properly choose M donors, which is maybe very small. It is very important because if we extend this to big data problem, then we cannot use all possible donors. It's too much. So we have to use M possible donors. We call that FHDI. So this is the example. For example, to cure this first row, we have only known information is on variable 4. Then we compare all the variable 4. And okay, these 3 will be the donor to cure this one. Of course, these 3 cases have different weight, how close it is to this missing pattern. And then question is, how can we get the weight then nicely? So we use the expectation maximization scheme, this existing method in statistics. So in short, we try to maximize to make the joint distribution as smooth as possible. We make the joint probability distribution as smooth as possible. This is the behind the story of this expectation maximization algorithm. So to do that, we need to investigate first. This is the pattern of the observed value, and this is 0.18 something is a joint probability of the entire group. This is a joint probability. So this is the after curing. For example, this is the 6 donors, and the donors gives different value for this Y4. Whereas when we use 5 donors, this is the possible imputed value for the Y4. So there's some theory about that. FHDI, although it uses only M donors, but as the data size increases, FHDI can asymptotically replace fully efficient cases. So it's very good property, asymptotic property, because when we deal with large data or big data, we can cure in a very robust way to cure this one. But the available R package is only for decent small size. So what if we want to cure large data, big data? So we need to develop a parallelized version for this FHDI. So initial version was to tackle this big N problem, that is the millions of instances, or big P problem, so millions of variable, high dimensional space. Combined, we call that ultra data, so big N and also big P. It's very challenging data set. So the initial version can tackle separately big N data or big P data. So it's already published at IEEE TKD 2020. Now the version 2, now we can tackle ultra data. It's accepted now, so it will be published in soon, 2023. Open source, so you can use it. So these are 4 key steps for the UPFHDI. So I just briefly mentioned that. Parallel cell construction, so about the categorize that one, and parallel EM algorithm, and parallel imputation, and then parallel variance estimation. I will talk about that later. So depending on the algorithm, we use the various parallel schemes such as divide and conquer, and then cyclic approaches. And also we found that we cannot use memory only because the data is very big now. So we inevitably use the hard drive data transfer. So we found OOPS libraries works very well. So that's this library's name, OOPS. We leverage that existing package to facilitate the hard drive data transfer. We found this very promising. The scalability for the big M problem is very promising. And then this is even when you have the ultra large data, say, for example, 0.1 million instances and then 10,000 variable. 10,000 variables. So it's very big size, but it shows good scalability. The last challenge we need to tackle was suppose we have millions of instances, the variables, very high dimensionality, and we have a lot of missing lists. Then how can we find donors? Because there are so many similar donors, possible donors. There are many methods. So so-called name of variable reduction. So we found very interesting, powerful, sure, independent screening method. The bottom line here is that suppose we know the true model of this linear equation, then if we select out variable merely by correlation score, then it gradually approaches the true model. So there is some theory about that. So we found this very interesting and powerful. In sum, suppose variable 3 has correlation score like this, sorted by, say, variable 10 is highest correlation score, variable 12 second, like that. For the Y4, we have a correlation score like this, Y9, Y12, Y100, so on and so forth, in descending order. So if we find intersection, then Y12, Y100 be very important for donor selection. And we simply used union or global ranking, so on and so forth. So this is the details algorithm for the union or intersection or global ranking. I just want to skip that. So then another important thing is that as an engineer and scientist, we want to know uncertainty, how accurate or how uncertain it is after data curing. The first popular method, so-called jackknife method, literally it delete one row and calculate result, and second row calculate result, so on and so forth. That's what we call jackknife method. And then, but it's very time consuming. It works very well for the small size, but we found that the so-called linearized technique can save a lot of time using this formula. So for example, horizontal axis tells you the number of variables. So less than variable, say 5, if the variable less than 5, the error inaccuracy is very high if you use the linearized technique. But more than 10 variable, the difference between jackknife, very good variance estimator, and then linearized technique is less than 5%. It's very fast. As you see here, for practical, so from medicine, genetics, transportation, biology, we tested this one. Jackknife method is very time-taking, as you see here, but the linearized technique is very fast, incredibly fast, but it's still very attractive compared to knife method. FHDI can improve the data curing incredibly. So validation, how can we validate this one? So as I mentioned, we tested a lot of data and then from various domains, including artificial intelligence domain, all the way to biology. By the way, these are all available in this data depot. So I'm happy to share this presentation. So I'm gonna, please contact the organizers and I'm happy to share this one. So bottom line here is that this is summary of the table. So GAIN is a generative adversarial imputation network. It's a deep learning style imputation method, very popular these days. We tested this, but for large data or high dimensional case, the GAIN for using the default setting aborted. So that means it cannot tackle the big data imputation. But our method, UP-FHDI, can nicely and stably cure the data. And it helps the accuracy of the data curing. The conclusion is that UP-FHDI, ultra large data oriented parallel FHDI, can cure the large data and only requires raw data itself. So it's very good for the engineers and scientists. And it can tackle millions of instances, big M problem, or more than 10,000 variable, big P problem concurrently. And as we showed in the paper, this way we can positively improve machine learning, the big data. What's the future then? I believe that some people still can say, we don't need data curing. Because we have big data, so I like the machine learning without data curing. It's okay, because it's tests, it saves a lot of time. But if the machine learning or statistical inference is used for critical decision making, then maybe we have to reconsider. Because by doing so, we can save a few percent or 20% machine learning prediction improvement. It may be very critical if it is related to biological or medical decision or the societal decision, it can be very critical. And also, we love to share this UP-FHDI. Although it's written in C++ and MPI, but we would like to share this open source code for other domain. So maybe you can embed this package in your own program or software or services, and somehow you can pre-cure your data set. Once again, our serial version program is already available, downloadable in the CRAN. So maybe you may have heard of it. So yeah, I'd like to acknowledge the generous support from the NSF. And then these are the papers. You can see more details and theories. And then there are a lot of links to the data and source codes. So love to share that one. Once again, thank you so much for this opportunity.